right, so we continue with finding surface integrals in another way. So remember when we did line integrals of vector fields? And then we used Green's theorem to calculate these. That one way of finding those line integrals was to use Green's theorem, but where the curve was closed, right? So just like with surface integrals, we will look at two other theorems for calculating the surface integrals. Use Stokes and the divergence theorem. Okay, so Stokes is another very important mathematician who contributed something to multivariable calculus. All right, so let's look at Stokes first and then the divergence. Stokes' theorem is a generalization of Green's theorem to 3 dimensions. Okay, so remember Green's theorem was in 2 dimensions, Stokes is in 3 dimensions. And as a matter of fact, both Stokes and divergence are in 3 dimensions. So we're doing triple integrals here. All right. So Green's theorem expresses a double integral over a plane region in terms of a line integral over the boundary of a closed region. We spoke about that. Stokes' theorem now expresses a surface integral in terms of a line integral over the boundary of the surface. So just like Green's, we must have orientation. So positive orientation means the boundary, on the boundary we go counterclockwise like Green's. And remember, for surface integrals, we always want upward normals as positive orientation. Let us look at Stokes' theorem. Let S be an oriented, piecewise smooth surface that is bounded by, here we go again, simple, closed, piecewise smooth boundary curve C with positive orientation. Let F basically, let's just say, by a nice curve. Okay? Nice encompasses all of these adjectives. Let F be a vector field whose components have continuous partial derivatives on an open region in R3 that contains S. Then the line integral over C of F dot dr is equal to the double integral over S of curl F dot ds. And this is Stokes' theorem. The line integral here is equal to, we're looking at a surface now, so it's a double integral of the surface S curl F dot ds. Now the important thing is, how do you work out this double integral of curl F dot ds? Go back to the integrals that we looked at in the last lecture, the formulas for surface integral. Let's look at them again. So if S is the surface z equals g of xy, then this is the formula that I gave you. The double integral over S of F dot ds is equal to the double integral, let's call the region D. I can't remember what I called it. What I said is that you replace z, write z in terms of xy, so write your entire vector field in terms of xy, dotted with this vector, which is the normal. And so when you work it out, this is a D again, it ends up being that. So remember we did that the last time. That's a formula. So this is what we are going to use to calculate this double integral of curl F dot ds. So therefore the double integral over S of curl F dot ds is equal to, again, the double integral over D of the same thing, minus P times these partials minus Q times the partial plus R dA. But this time, what is P, Q, and R? P, Q, and R are the components of curl F. So you see above here we had an F, right? The double integral of F. So the components P, Q, and R here, these were the components of F. But here we have curl F. So the components P, Q, and R are the components of curl F. Okay? So you need to find curl F. So again, I wrote down the formula for you. All right, so let's do an example. So I need to write out, let's write out the formulas that I just wrote a while ago. Do I have enough space? Let me write it on top of that. I suspect I will not have space. So what I had is that the double integral of S of curl F dot ds is equal to the double integral over D. And did I have a minus P partial G of X? Just make sure I have this. Minus Q partial G of Y plus R. Is that what it is? Is that the formula I have? That's it? And P, Q, and R, remember, are the P, Q, and R components of curl F. And then let me also write the definition of curl F. We need that. It is partial R partial Y minus partial Q partial Z I plus partial P partial Z minus partial R partial X G plus partial Q partial X minus partial P partial Y G. Okay? Did I make an error? Okay, thanks. Okay, we might have to, so we're going to use these formulas. Okay, let's look at this question now. Use Stokes' theorem. So remember again, you are still finding surface integrals. So this method that I taught you the last time, you can use it for all of the questions we're going to do today. But if I specify that you have to use Stokes' theorem, please use it. Okay, let's do it. Use Stokes' theorem to evaluate this line integral, let's say over C, equals the double integral over S of curl F dot ds, where F is this vector field and S is the part of the cone Z equals square root of x squared plus y squared between the planes Z equals 1 and Z equals 3, and with upper unit normal vectors. Okay, the first thing we should do is to calculate curl F. Alright, so let's do that. So in F, so I don't want to confuse these P, Q, and R, but in F, P is YZ, Q is minus XZ, and R is Z cubed. Okay, let's find curl F. So the formula is right up there. Let's do it. Partial R with respect to Y, 0, minus partial Q with respect to Z is minus X, so that's a plus X, I, plus partial P with respect to Z is Y, minus partial R with respect to X is 0, J, plus partial Q with respect to X is minus Z, minus partial P with respect to Y is Z. Okay. So curl F is really the vector X, Y, minus 2Z. Okay? Okay, so that's the curl. Now we need to find our normal vector. That will be the minus partial gx minus partial gy and 1. Okay, I mean I didn't write it up here, right here, but just know what you're doing. It's on the opposite page. You are dotting curl F with the normal. That's how I end up with this formula. So we need to find these two partials here. What is our G, by the way? Our G of x is this z equals square root of x squared plus y squared. So that's what we have to partially differentiate. So I could have easily have written, instead of partial G partial x, partial z partial x. Okay? Okay, so let's go. So z equals square root of x squared plus y squared, which is x squared plus y squared to the half. Let's find the partials. Partial z with respect to x, that's a half. We're using the chain rule here, right? A half times x squared plus y squared to the minus a half, and we multiply by 2x. And this ends up being x over the square root of x squared plus y squared. And if you do the same thing for partial z with respect to y, you get y over square root of x squared plus y squared. Okay? Alright, so now let's set up the integral. So, the double integral over S of curl F dot ds, right? The rule is the double integral, let's call it D. So you take your curl F, X, Y, oh, what are we missing? What should we have done up there? Here, and after you find curl F, what do you notice? There's a 2z, right? Remember what I told you about the z? We need to replace z. And put it in terms of x, right? And y. And we have it up there. So it's square root of x squared plus y squared. So put that to the side. X, y minus 2 square root of x squared plus y squared. Okay? Okay. Where was I? Okay, so let's write this. So that's minus 2 square root of x squared plus y squared. And then we are dotting this with the normal, which is minus z partial x. So that's minus x over square root of x squared plus y squared. Then the minus zy, so that's minus y over square root of x squared plus y squared, comma 1, dA. We'll put the limits later on, okay? Make sure, you know, when you're doing these things, put your limits at the last step. So work out the integrand, because your integrand may work out to be something so easy. Maybe you might have to change your limits, okay? Let's do that dot product now. Okay, what do we have here? We have minus x squared over square root of x squared plus y squared. We have minus y squared over square root of x squared plus y squared. And we have minus 2 square root of x squared plus y squared. All of that is dA. Now you need to simplify that, please. The first two terms work out to be minus x squared plus y squared all over square root of x squared plus y squared minus 2 square root of x squared plus y squared dA. Simplify further. This is the double integral over D of minus square root of x squared plus y squared minus 2 square root of x squared plus y squared dA, which works out to be the integral over D of minus 3 square root of x squared plus y squared dA. Okay, any questions? Now we need the limits, but look at what we have here. Look at the type of integrand we have there. What do you suggest we do? Polar. Yeah, that's polar. Okay. So let's see the limits for r and theta though. Theta is always easy. So polar. So theta goes from 0 to 2 pi. That's easy. But look at what r is. Now, how do we get r? Very good. Z equals 1 and z equals 3. So put that into your z. So that means square root of x squared plus y squared equals 1, right? And square root of x squared plus y squared equals 3. But in polar coordinates, what is square root of x squared plus y squared? R, right? So therefore r goes from 1 to 3. So I hope you've seen the trick of using polar. It makes it so much easier. Okay, so what does your integral become? 0 to 2 pi, 1 to 3. What is that integrand going to be? Minus 3 times r, and what else? And r, so that's r squared, good. dr d theta. You with me? Isn't that a lot better and easier? Okay, integrate. Now we can do that. We don't have to use our calculator for that. How much space do I have? Can I? This is equal to 0 to 2 pi. When you integrate that, you get minus r cubed from r equals 1 to r equals 3. I'm going to use the same line, okay? Which is 0 to 2 pi. This works out to be, I think, minus 26 d theta, which is minus 52 pi. Okay, so that's this one. Let's do another. Use Stokes' theorem to evaluate. Let's put this C again and let's put this S. Curl F dot ds, where F is this vector field and S is the part of the plane x plus 2y plus z equals 2 that lies in the first octant with upper unit normal vectors. Now you see the fact that I just see the way that plane is written, I know I'm not going to use polar. Okay? So that should be a clue. But anyway, we need to start from scratch. Oh, we need to find our curl F. So go back. You have the formula in front of you, right? The curl F. I'm not going to write it again. Okay? So in F, P is y minus x, Q is x minus z, R is x minus y. Let's find curl F. So refer to your formula, all right? Curl F. Okay, partial r with respect to y, tell me. Partial y r with respect to y, negative 1, minus partial q with respect to z, negative 1, so that's a plus 1, I, plus partial p with respect to z, 0, minus partial r with respect to x, 1, j, plus partial q with respect to x, 1, minus partial p with respect to y, 1, k. So this is the vector 0, minus 1, 0. Okay. Now, we need to find the partials. Partial of z with respect to x. So take this plane, solve for z. So z is equal to 2 minus x minus 2y. Okay. Now let's find the partials. Partial z with respect to x, tell me. -1. Partial z with respect to y. -2. Okay. Let's set up the integral now. So the double integral over s of curl f dot ds is equal to double integral over d. As I said, put in your limits later, okay? What are we doing? Curl f. Put that vector here, 0, -1, 0, dot with. What is your normal? What do you dot it with? Remember what I told you? Not 0. 1, 2, 1. Right? Because it has to be, you have to negate these first partials. Right? And then 1 is always the last vector. dA. What is that ended up being? -2? Now, what are your limits? Now, here we have, definitely have to project this into the xy plane. So we're going right back to whenever we did that, okay? So look at, go back. It lies in the first octant, right? So first octant is like first quadrant, good? So in other words, your z is all positive, right? Greater than or equal to 0. So what you're going to do is you need to project this into the xy plane, this plane here, x plus 2y plus z equals 2. So what you do, you set z equals 0, right? And graph the line. Good? So if you project it into the xy plane, because this is already in the first octant, when you project it into the xy plane, it should now lie in the first quadrant. Okay? So let's see what we're going to get here. So x plus 2y plus z equals 0. X plus 2y plus z equals 0. So we want to set z equals 0. Is it 0? Did I write 2? Okay, thanks. 2. Set z equals 0, x plus 2y equals 2. Okay, so we're going to draw that. So I didn't write it there, but maybe you can write on your sheet what we're doing. We're finding limits. Good? And how are we finding limits? We are projecting into the xy plane. All right? So let's draw. Okay, so when x is 0, y is 1. When y is 0, x is 2. And we are in the first quadrant. Okay? So this here, let me just put it in y. I'll solve for y. This line is y equals what? 1 minus a half x? Okay? Alright, so now this is our region D. Good? So we want it to be, it doesn't matter if it's horizontally or vertically simple. Let's make it vertically. Okay, so you're ready to write in the limits now. What do we have? So minus 2 dy dx. What are your x limits, please? 0 to 2. What are your y limits? 0 to 1 minus a half x. Good job. All right. Now this you have to integrate. When these integrals are that easy, please show your work. 0 to 2. We integrate in respect to y minus 2y. And y goes from 0 to 1 minus a half x dx. How much space do I have? Okay, 0 to 2. Put 1 minus a half 2x. What do we have here? Minus 2 plus x, is it? Is that right? Okay. Dx. integrate minus 2x plus x squared over 2 0 to 2, which is minus 4 plus 2 minus 2. So that's Stokes. Any questions? Let's do the divergence. Okay, so let's move on to divergence. So I think I made a small error a while ago when I told you triple integrals was for both Stokes and divergence. Sorry, triple integrals is for divergence. Okay, Stokes was double. Okay, so let's do this. So again, you can also use the divergence theorem to work out a surface integral, but there are conditions. The surface has to be closed. Remember, just like Green's theorem was, closed curve. This theorem enables us to convert a surface integral over closed surface into a triple integral over the enclosed surface. Okay, here is the divergence theorem. And another word for the divergence theorem, it was actually Gauss. Gauss is another important mathematician. It's Gauss who discovered this. Divergence. Let W be a solid region in R3 whose boundary S is a piecewise smooth surface such that S is given outward orientation. Okay, and this is going to be our positive orientation. Let F be a vector field on a region containing W. Here is the divergence theorem. This surface integral, the same surface integral we've been looking at, f dot ds, is a triple integral over W, the solid region of div f, dv. So that is why they call it a divergence, because you use div. And what is div? Recall, div f is the sum of these partials. Okay? All right. So let's do some questions here. All right, so again, let me write out the formula here. S of f dot ds, that surface integral, is equal to the triple integral over W of div f dv, where div f is partial p with respect to x plus partial q with respect to y plus partial r with respect to z. Okay? All right, let's do it. Use, again, if I ask you to use the divergence theorem, please use it. And the reason is usually, if I ask you to use the divergence theorem, it's easier to work out that surface integral using the divergence theorem instead of methods you learned before. All right? So use the divergence theorem to evaluate the surface integral. S is given positive orientation. So here is your vector field, x, y, z, and S is the spherical surface of this particular equation. All right. So the first thing we need to find is div f. This is a lot easier than Stokes, by the way, because curl f has a lot more. It's more, but this more intricate. But this is easier. Let's find div f. So look at the formula for div f. So remember what your p, q, and r are. I didn't write it down, but p is x, q is y, and r is z. Okay. So tell me, what is div f? What's partial p with respect to x?
2x. 1.
It's 1. What is partial q with respect to y? Partial r with respect to z? 1 again. So that's 3. Okay, so set up the integral. So what we're saying is that the surface integral of f dot ds is equal to the triple integral over W of 3 dV. But what is W? What kind of surface is W? It's a sphere, right? Now, by the way, let me write this as, and you will see why I'm trying to look for shortcuts and tricks. I'm going to take this 3 and put it outside the integral. 3 what is the triple integral of 1? Volume. So this part here is really finding the volume of the sphere. X squared plus y squared plus z squared equals 1. Right? What is the volume of a sphere? Do you remember the formula? 4/3 pi r cubed. You see? So I would not have integrated this. If you can recognize that, just do that. What is the radius of that sphere? 1. So that is equal to 4/3 pi times 1 cubed, which is 4/3 pi. And so we're almost done. So the double integral over S f dot ds is equal to 3 times 4/3 pi, which is 4 pi. I hope you see why the divergence theorem made this a lot easier. If I ask you now to go and do this using methods you learned in the last lecture, it will take you a longer time. Okay? All right. So that's that one. This one now. So you have this vector field. What is S? Is the surface of the solid bounded by these lines. What type of solid is that, by the way? Not a solid. Can't be square. Go further up here in 3D. Cube. Right? Okay. So we have to integrate over this cube. Okay, let's do the div thing. Div F. So I'm not going to write out the formula again. So you tell me, what is partial P with respect to x2 plus what's partial Q with respect to y? X squared. Partial R with respect to z? Negative 2xz. So this is what we are integrating. So this over S of f dot ds is the triple integral over W of 2 plus x squared minus 2xz dv. Now let's put in the limits. We cannot do volume or anything like that here, right? We have to go the long route and integrate. The limits are quite easy, yeah? They're all constants. X goes from 0 to 1, y goes from 0 to 1, z goes from 0 to 1. Makes it quite easy. So put them in. 0 to 1, 0 to 1, 0 to 1, 2 plus x squared minus 2xz. Doesn't matter the order. dz, dy, dx. Okay? Now for something that easy, please go through it. Show all your work. So let's go. Let's integrate with respect to z. Can you tell me what it is, please? 2z, x squared z. Very good. And z goes from 0 to 1, dy, dx. Okay, let's substitute. The z equals 0 is going to give us 0, so let's just substitute 1. We have a 2 plus x squared minus x. dy dx. Go again. Integrate with respect to y, please. Tell me what you have. 2y x squared y minus what? xy. Y goes from 0 to y equals 1 dx. Substitute y equals 1 again. That's all we need. 2 plus x squared minus x again, which is not surprising. Dx. Final integration. 2x plus x cubed over 3 minus x squared over 2. 0 to 1. And when you put 1, you get 11 over 6. Any questions? Next. Now, look at this. This is the vector field, you see it? And look at S. S is the surface of the cylindrical solid whose boundary is that. Now look at this solid. Yeah? What should come to you? I mean, you have to set up the integral of div, but what do you think? You might have to eventually put it in polar. Okay? So let's go. Div. Give me div, please. Sweet. Alright, set it up. The double integral over S of f dot ds is the triple integral over w of 3x squared plus 2y squared plus 2z. Say that again. 3. Thank you. dv. Okay, now it's not polar, by the way. We're in triple integrals, so it's not polar, it's cylindrical, right? Okay, so let's get our limits. So we're going to use cylindrical coordinates. What are our z limits? 0 to 1. What are our r limits? 0 to 2, beautiful. And theta? 0 to 2 pi. Okay, let's convert. Let's do the integrand first, and then we're putting our limits. The integrand in there. What is the 3x squared plus 3y squared? Convert that to what? 3r squared. You're on a roll. You're doing so good. 2z, right? Leave the 2z because we're in cylindrical, okay? What else? Times r. Now, remember for cylindrical, we need dz, dr, d theta, 0 to 1, 0 to 2, 0 to 2 pi. Okay. Again, I would advise you to work that out, okay? Let's distribute that. I think it would be easier if we distribute. 0 to 2 pi, 0 to 2, 0 to r, 3r cubed, plus 2zr, dz, dr, d theta. Okay, let's go. Integrate with respect to z. What do you get? 3r cubed z, yes. Plus z squared r, beautiful. Z goes from 0 to 1. Dr d theta. Substitute 1. 0 to 2 pi, 0 to 2, 3r cubed plus r, dr d theta. Integrate with respect to r now. Tell me. 3/4 r to the 4th, r squared over 2. R goes from 0 to 2, d theta. Okay, what's that? You did it? 13? 13? 13 d theta. You sure it's 13? I'm getting 14. 14, right? And so the final answer is 14 times 2 pi, which is 28 pi. Okay, so you see, I did a question. You still have to use the divergence theorem, but you have to convert to cylindrical. So be aware of these type of questions, okay? Any questions? Number 4. Here is another vector field, and the surface, this is the surface of the spherical solid E in the first quadrant, first octant, enclosed by z equals the square root of 4 minus x squared minus y squared, and z equals 0. Now, again, just reading the question should tell you something. The solid is a sphere. You will eventually have to convert to spherical to be easier. Okay? Okay, let's go. Let's do it. Give me div f. Very good. And I mean, even though you didn't think so, just looking at what div f is, because you remember that x squared plus y squared plus z squared is rho squared, right? In polar, and spherical. Set it up. The double integral over s of f dot ds is a triple integral over w of 3x squared plus 3y squared plus 3z squared dv. So as you said, we are going to use spherical coordinates. Okay, we need to work out what rho is if you cannot see it. So let's take the this is a sphere, but let's just see that it already is a sphere. Z equals the square root of 4 minus x squared minus y squared. And the only reason they wrote the sphere looking like that with that type of equation is because we're in the first octant. So they wanted to show that z was positive. Okay? So square both sides. What do we have? Z squared is 4 minus x squared minus y squared, which is very good. So the sum of the squares is 4. So right away, I'm sure you can tell me what rho is now. What are the limits for rho? 0 to 2. What are the limits for theta? 0 to 2 pi. What are the... Hold on. Aha, thank you. Why? First octant, thank you. And similarly, what is the phi? No, we're in the first octant. So it cannot be 0 to pi. No, it's pi over 2. Don't forget, what is phi? Phi is the angle between the positive x-axis and the line, right? So yeah, I think that's the first time we did something like that in the first octant, right? Okay, shall we set up? Okay, and the reason, put a note that the reason, let me put it here, that this it's in the first octant. That's why. Let's set up. So what do we have? I'm going to put the 3 outside if you don't mind. Okay, what is that integrand going to be?
Rho squared.
Just rho squared. What is our Jacobian? Sine phi. Okay, so d rho d theta. I can't remember what order I use, but it really doesn't matter because they are all constants, right? 0 to 2, 0 to pi over 2, 0 to pi over 2. Okay, let's simplify that, and this should not be too hard to integrate. 3, 0 to pi over 2, 0 to pi over 2, 0 to 2. So that's rho to the 4th. Sine phi d rho d theta d phi. Okay, let's do this. Integrate with respect to rho. Rho to the 5th over 5 sine phi. Rho goes from 0 to 2 d theta. Okay, put 2. So when you put 2, is that for 32 over 5? Okay. With respect to theta now, it's just, so all of this is now constant because we integrated now with respect to theta. So that's theta times 32 over 5 sine phi. Theta goes from 0 to pi over 2. Okay, put pi over 2 in there. What's that? 16 over 5 pi sine phi d phi. Integrate. Three times minus 16 over 5 pi cosine phi from 0 to pi over 2. Okay, what's that, pray tell? Cosine of pi over 2 is what?
So cosine of 0 is 1.
Oh yeah, we're not finished yet. Thank you very much. So that's 3, so that's a 0 minus, and cosine of 0 is 1, so that's a plus 16 pi over 5. Oops. And this is 48 pi over 5. Okay, let's go on. So this one I want you to do, but I just want you to pay attention to a word in there. Find the flux of the vector field zyx over the unit sphere and use the divergence theorem. Do not get confused when you see flux. Flux is the same thing as the surface integral. Okay? So do this one on your own. Find the surface integral. It should not take you long. Okay, so let's do this. Give me div. Give me div.
Wait, it'd be 0. It'd be 1.
What's that?
Because it's the zy axis.
What is the formula for div?
It's p sub x.
Partial p with respect to x.
0.
0 plus partial q with respect to y is what? 1. Right. Partial r with respect to z is 0. So that's 1. Are you with me?
Yes.
Now let's find that. That's your flux, right? Set it up. That's dV. Good? Which is what? Of what? The volume of this unit sphere. Which is what? Pi. And what is the radius? 1. So that's 4 over 3 pi. Okay. Okay, the last one, I want you to do it too, but I only want you to set it up. Set up the integral, okay? So set up the integral, and now notice I did not tell you to use the divergence, but I want you to use the divergence theorem, okay? And then I want you, after you have set up the integral, set it up in cylindrical coordinates. All right? So let me remove that. And if I did not tell you, what should have been your guide? X squared plus y squared equals 9. You have a cylinder there. Okay? So set up the integral in cylindrical coordinates. Don't evaluate it. You can just set it up. Let's do it. Can somebody give me div f, please? 0 plus 2y plus 0, which is 2y. Fantastic. How is that? Set up the integral now. So that's your flux, is equal to the triple integral over w. And again, we're using the divergence theorem because it's a closed surface of 2y dv. Now, as I said, we're using cylindrical coordinates, so let's do this. Let's start. What are the coordinates for r? Let's go here. 0 to 3, theta, 0 to 2 pi, z. Very good. So it's 0 to y minus 3y, right? But we need to convert to cylindrical. So y is r sine theta minus 3. You with me? Good. So now let's do this. What does the integral become? Let's do the integrand first. 2y becomes? And what else? So you need to put a squared, right? dz, dr, d theta, 0 to r sine theta minus 3, 0 to 3, 0 to 2 pi. How is that?
Perfect.
Okay, thank you.